cosm. Whoosh.
Around this brilliant star, planets orbit in their precise, well-choreographed paths, each one a distinct world with its own character and mysteries. Earth resides in this relatively comfortable neighborhood, where sunlight is abundant and temperatures allow for the miraculous phenomenon we call life. But venture outward beyond the orbits of the 8 planets, past the rocky remnants that circle in the asteroid belt, and something extraordinary happens. The light from our sun begins to fade. The temperature drops precipitously. And the very definition of what constitutes our solar system becomes increasingly blurred and uncertain. For centuries, humanity believed that the solar system ended with Neptune or perhaps Pluto, that distant ice world that astronomers only recently demoted from planetary status. We imagined a kind of cosmic boundary, a fence that marked where the sun's domain ended and the vast emptiness of interstellar space began. But reality, as it so often does, proved far more complex and magnificent than our initial understanding. The solar system does not end where we once thought it did. Instead, it extends far, far beyond the orbits of the outermost planets, reaching into a realm so distant that light from our sun becomes merely one star among billions in the night sky of that hypothetical vantage point. This outer frontier is not empty. It is not barren or devoid of interest. Rather, it is a realm populated by countless icy bodies, mysterious remnants from the formation of our planetary system billions of years ago. It is a region of immense scientific importance, a cosmic archive that holds clues to understanding not only our solar system's history, but also the nature of planetary formation itself. This is the story of what exists beyond the familiar worlds we know, in those deep and distant regions where our sun's influence gradually fades into the background radiation of the universe. The first thing we must understand is the true scale of the solar system. When we look at diagrams in textbooks and on the internet, we see the sun at the center with 8 planets arranged around it like pearls on a necklace. These diagrams are, of necessity, not to scale. If they were truly to scale, with Pluto shown at the correct distance from the sun, the planets would appear as invisible specks, and the entire diagram would need to be the size of a football field or larger. The human mind struggles to comprehend such distances. We use numbers like millions and billions of kilometers, but these figures become abstractions, losing their meaning through sheer magnitude. Consider this: light from the sun takes approximately 8 minutes to reach Earth. It takes about 40 minutes to reach Jupiter. Yet it takes nearly 5.5 hours to reach Pluto. And Pluto, once considered the last true member of our planetary family, is not remotely close to being at the edge of the solar system. In fact, Pluto is merely the outermost known planet, a boundary marker of sorts, but the true edge lies vastly farther out. If we were to place the sun at one end of a football field, the 8 planets would crowd within the first 10 yards. But the solar system would extend far beyond the opposite end of the field. It would stretch into the parking lot, across the street, and continue for many city blocks beyond. Beyond Neptune's orbit lies a region called the Kuiper Belt, named after astronomer Gerard Kuiper, who predicted its existence in the 1950s, though it was not actually observed and confirmed until the 1990s. This belt is home to thousands upon thousands of icy bodies, ranging in size from tiny asteroids to objects as large as or larger than Earth's moon. These are not rocks, as many asteroids in the inner solar system are, but rather primordial remnants composed primarily of frozen volatiles, water ice, methane, ammonia, and other substances that exist in solid form only in the extreme cold of the outer solar system. Pluto itself, despite its demotion from planetary status, is one of the largest and most fascinating objects in the Kuiper Belt. The discovery of Pluto in 1930 by Clyde Tombaugh was considered one of the great achievements of astronomy. For nearly 8 decades, it held the distinction of being the 9th planet, a status that gave it a special place in public imagination. Children learned about the 9 planets, and Pluto, with its small size and distant orbit, captured the imagination as the mysterious, lonely world at the edge of civilization. Then, in 2006, the International Astronomical Union redefined what it meant to be a planet, and Pluto fell short. The decision was scientifically sound, Pluto is far too small to have gravitationally cleared its orbital neighborhood of other objects, the key criterion for planetary status, but it struck an emotional chord with the public. Suddenly, Pluto was demoted to dwarf planet, and millions of schoolchildren had to relearn the composition of the solar system. But Pluto's demotion actually reveals something profound about our expanding knowledge of the cosmos. Pluto is not alone out there. It is merely one of thousands of similar bodies. The Kuiper Belt is crowded with dwarf planets and large icy bodies. Among these, objects like Eris, Makemake, Haumea, and Gonggong have been discovered and studied. Eris, in particular, captured astronomers' attention because it is actually more massive than Pluto, despite being slightly smaller in diameter. The existence of Eris and other large Kuiper Belt objects provided the impetus for the reclassification of Pluto. It became clear that there were many Plutos out there, and to grant them all planetary status would be arbitrary and confusing. The Kuiper Belt extends from Neptune's orbit, at approximately 30 astronomical units from the Sun, to about 50 astronomical units. An astronomical unit, or AU, is defined as the average distance from Earth to the Sun, approximately 150 million kilometers. So the Kuiper Belt spans a region from about 4.5 billion kilometers to approximately 7.5 billion kilometers from our star. Within this region, tens of thousands of known objects orbit, and astronomers estimate that there could be as many as 100,000 or more objects larger than 100 kilometers in diameter. Countless smaller objects also populate this region, perhaps numbering in the millions or billions. These icy bodies are not merely geological curiosities. They hold profound significance for understanding the history of the solar system. About 4.5 billion years ago, our solar system formed from a collapsing cloud of gas and dust. Gravity pulled the material together, and the vast majority of the mass accumulated in the center, forming the Sun. The remaining material formed a rotating disk around this young star, and within this disk, planets began to coalesce. The inner solar system, being warmer, allowed only rocky materials to accumulate into planets, which is why Mercury, Venus, Earth, and Mars are relatively small and rocky. But farther out, where temperatures were cold enough for volatile compounds to remain solid, much larger planets could form. Jupiter and Saturn, the gas giants, accumulated enormous quantities of material and became the dominant gravitational influences in the outer solar system. The formation of these giant planets had profound consequences for the Kuiper Belt. As Jupiter and Saturn grew, their immense gravitational field stirred up the region around them, scattering smaller objects and clearing orbital zones. This process, known as planetary migration, likely caused the giant planets to shift positions over millions of years. In doing so, they scattered countless icy planetesimals, the building blocks of planets that never fully coalesced, outward into what became the Kuiper Belt. This explains why there are so many objects out there today. They are the debris of this ancient gravitational chaos, fragments that survived and continue to orbit the Sun to this day. One of the most intriguing aspects of the Kuiper Belt is its connection to comets. For a long time, astronomers were puzzled by the source of periodic comets, those icy visitors that occasionally venture into the inner solar system, where the Sun's heat causes them to develop their characteristic glowing tails. It was theorized that a cloud of comets must exist somewhere beyond the known planets, a reservoir from which comets were occasionally dislodged and sent spiraling inward. The Kuiper Belt is now understood to be the source of short-period comets, those with orbital periods of 200 years or less. When a Kuiper Belt object is gravitationally perturbed by a neighboring object or by the passage of a nearby star, it can be knocked from its orbit and sent on a new trajectory that brings it into the inner solar system. The comets that result from this process are among the most spectacular objects in the sky. As they approach the Sun and feel the increasing warmth, the frozen volatiles on their surfaces begin to sublime, to transform directly from solid to gas, bypassing the liquid phase. This creates a rapidly expanding cloud of gas and dust around the comet's nucleus, called a coma. Radiation from the Sun and the solar wind, streams of charged particles flowing from the Sun, push this material away from the comet, creating the famous glowing tails that can stretch millions of kilometers into space. These tails always point away from the sun, regardless of which direction the comet is traveling, because they are pushed by the solar wind rather than being left behind like exhaust from a rocket. Beyond the Kuiper Belt lies another region of profound mystery and scientific interest, the Oort Cloud. This is not a well-defined region with a sharp boundary, but rather a diffuse halo of countless icy objects surrounding the solar system. Named after astronomer Jan Oort, who proposed its existence in 1950, the Oort Cloud represents the true outer limit of the Sun's gravitational influence. While the Kuiper Belt extends to roughly 50 AU from the Sun, the Oort Cloud is thought to extend from approximately 2,000 AU to as far as 200,000 AU from our star. To put this in perspective, 200,000 AU is approximately 3 light-years, a distance so vast that light from the Sun, traveling at 300,000 kilometers per second, takes 3 years to traverse it. The Oort Cloud is not a dense region like the Kuiper Belt. The objects within it are separated by enormous distances from one another. If an object in the Oort Cloud were somehow transported to Earth's orbit and observed through our most powerful telescopes, it would appear as a dim star, if it were visible at all. Despite this diffuse nature, the Oort Cloud is estimated to contain billions or even trillions of icy objects, making it one of the most populous regions of the solar system in terms of object count, even if they are spread across an incomprehensibly large volume of space. The total mass of the Oort Cloud is believed to be several times the mass of Earth, a considerable amount of material scattered across a region millions of times larger than the inner solar system. The objects that populate the Oort Cloud are thought to be remnants from the early days of solar system formation. They represent planetesimals that never became part of a larger body but instead were ejected into this distant region by gravitational interactions with the giant planets. Some may have come from even farther away, from regions near where Jupiter formed, before being flung outward by the complex gravitational dance of planetary migration. These objects have spent billions of years in the Oort Cloud, orbiting the Sun in the deepest darkness, never receiving significant warmth from our distant star, frozen in a state that has changed little since the time of their formation. The Oort Cloud is responsible for long-period comets, those objects that can take thousands or even millions of years to complete one orbit around the Sun. When a passing star or a gravitational perturbation from within the Oort Cloud itself dislodges one of these objects, it can fall toward the Sun, entering the inner solar system where it becomes visible as a spectacular comet. Famous examples include Comet Hale-Bopp, which last appeared in 1997 and will not return for another 2,400 years, and Comet Hyakutake, which graced Earth's night sky in 1996. These great comets are often the most impressive, their tails spanning enormous arcs across the sky, visible even to the naked eye. But the Oort Cloud is more than just a source of periodic comets. It is also a cosmic shield, a protective boundary that absorbs the occasional threats from interstellar space. The Oort Cloud is occasionally disturbed by the gravitational effects of nearby stars in the Milky Way galaxy. As our solar system drifts through space, following a complex path around the galaxy's center, it occasionally passes close to other stars. These close encounters can gravitationally perturb objects in the Oort Cloud, sending them on new trajectories. Most of the time, this results in comets being sent outward, away from the solar system entirely, but occasionally, objects are knocked inward, toward the Sun and planets. Some scientists have speculated that rare, catastrophic impacts on Earth throughout its history may have been caused by objects from the Oort Cloud, disturbed by the gravitational effects of passing stars. Beyond even the Oort Cloud lies the heliopause, the boundary where the Sun's gravitational influence gives way to the much weaker influence of the galactic center and the vast interstellar medium that fills the space between stars. This boundary is not sharp but rather a gradual transition, much like the edge of Earth's atmosphere, which gradually fades into space rather than ending abruptly. The heliopause is situated at roughly 100,000 AU from the Sun, a distance that would take a spacecraft traveling at the speed of modern space probes approximately 17,000 years to reach. Within the Oort Cloud and in the region between the Oort Cloud and the heliopause exists the solar wind, an invisible stream of charged particles flowing outward from the Sun at approximately 400 kilometers per second. This wind is created by the extreme heat of the Sun's corona, the outer layer of the solar atmosphere, which paradoxically is hotter than the Sun's surface. The solar wind extends throughout the solar system and beyond, creating what is called the heliosphere, a protective bubble of solar wind that shields the inner solar system from the more energetic cosmic rays that permeate interstellar space. The heliopause is the boundary where the pressure of the solar wind is balanced by the pressure of the interstellar medium beyond. In the region beyond Neptune and beyond the Kuiper Belt, space becomes an increasingly alien environment. Temperatures drop to within a few degrees of absolute zero, the coldest possible temperature in the universe. At these extreme temperatures, gases that would be familiar to us as air at the surface of Earth become solid. Nitrogen freezes. Oxygen freezes. Even hydrogen and helium, which remain gaseous even at temperatures near absolute zero in the laboratory, are present in minute quantities in the thin interstellar medium. Sunlight becomes so faint that an object there would receive as much light from the stars as a person on Earth would receive from a single candle held several kilometers away. Yet despite these harsh conditions, the region beyond the Kuiper Belt is not entirely empty or barren. Besides the icy bodies of the Oort Cloud, there is the sparse interstellar medium, clouds of gas and dust that drift through the space between stars. These clouds are far less dense than anything on Earth. A cloud of interstellar gas that stretched from Earth to the Sun would contain less material than a single grain of sand. Yet, in the vast volumes of interstellar space, these clouds accumulate into regions of significance. Some of these clouds are visible from Earth as dark nebulae, silhouettes against the brighter background of more distant stars. Others, illuminated by nearby stars, appear as luminous emission nebulae, glowing with the light of hydrogen and other elements energized by stellar radiation. The nature of the boundary between the solar system and interstellar space is itself a matter of ongoing scientific debate. Some astronomers define the edge of the solar system as the heliopause, the boundary of the heliosphere. Others argue that the solar system should be defined as extending as far as the Oort Cloud, since those objects are gravitationally bound to the Sun. Still others propose different boundaries based on different criteria. This ambiguity reflects the continuous nature of space itself. There is no fence, no wall, no marked boundary. Instead, the solar system gradually transitions into the interstellar medium, with the Sun's influence gradually fading but never completely disappearing, even at incomprehensible distances. The study of the outer solar system and the Oort Cloud is not merely an academic exercise. It has profound implications for our understanding of planetary systems around other stars. Astronomers have now discovered thousands of exoplanets, planets orbiting stars other than our Sun, and many of these systems show evidence of possessing structures analogous to the Kuiper Belt and possibly the Oort Cloud. This suggests that our solar system, with its orderly arrangement of planets and its comet-filled outer regions, is not unique but rather representative of a common pattern in the universe. By understanding the structure of our own solar system, we gain insights into how planetary systems form and evolve throughout the cosmos. Moreover, the discovery of objects beyond Neptune has profoundly changed our understanding of planet formation. For much of the 20th century, the theory of planetary formation was relatively straightforward. The solar nebula, the rotating disk of gas and dust from which our solar system formed, gradually condensed into planets through the process of accretion. Smaller objects collided and stuck together, forming larger ones, until planetary-sized bodies emerged. This theory worked reasonably well for explaining the inner planets, but became increasingly problematic when applied to the outer planets. Jupiter and Saturn, for instance, are too massive to have formed through accretion at their current locations in the time available before the solar nebula dissipated. The discovery of objects in the Kuiper Belt and the evidence for ancient planetary migration provided a solution to this puzzle. According to modern planetary formation theory, the giant planets formed in a different configuration than they currently occupy. Jupiter may have formed closer to the Sun, and as it grew, its gravity stirred up the disk of planetesimals, scattering some inward and some outward. Saturn and the ice giants, Neptune and Uranus, also migrated from their original positions. This great rearrangement of the outer planets scattered countless planetesimals throughout the outer solar system, creating the Kuiper Belt and the Oort Cloud as we observe them today. The process of planetary migration was not a gentle affair. It was a period of cosmic violence and chaos, a time when the solar system was fundamentally reshaped by gravitational interactions. The evidence for this ancient cataclysm is preserved in the current structure of the solar system. The Kuiper Belt and Oort Cloud are cosmic archives, storing information about events that occurred billions of years ago, when our solar system was young and dynamic. One of the most exciting discoveries in recent decades has been the detection of objects in the Kuiper Belt and beyond using advanced telescopes and surveys. The Hubble Space Telescope, the Spitzer Space Telescope, and ground-based surveys like the Sloan Digital Sky Survey have revealed that the outer solar system is far richer in objects than previously imagined. New dwarf planets are discovered regularly. Unusual objects with strange orbital characteristics have been found, some of which have puzzled astronomers. In 2016, astronomers discovered evidence for a ninth large object in the outer solar system, christened Planet 9, which has never been directly observed but whose existence is inferred from the gravitational effects it appears to exert on other objects. The search for Planet 9 continues, and its discovery would represent one of the greatest advances in planetary astronomy in recent history. The study of the outer solar system also has implications for understanding threats to Earth. While asteroids from the inner solar system rarely threaten our planet today, the evidence suggests that in the past, Earth has been struck by much larger objects. The extinction of the dinosaurs 66 million years ago was caused by the impact of an asteroid roughly 10 kilometers in diameter. Such large objects are rare, and direct impacts from the Kuiper Belt are even rarer, but the possibility exists that future impacts could occur. Understanding the populations and orbital characteristics of objects in the outer solar system helps us assess the risk of future impacts and plan for potential hazards. Furthermore, the outer solar system may hold secrets relevant to the search for life. While life as we know it requires liquid water, and this is difficult to imagine existing on icy bodies in the Kuiper Belt or Oort Cloud, it is possible that some of these objects harbor subsurface oceans beneath their icy crusts. If such oceans exist and contain the right chemical conditions, they might harbor microbial life. Such life would be fundamentally different from anything on Earth, existing in total darkness, relying not on sunlight but on chemical energy derived from interactions between rock and water. This possibility, while speculative, is not beyond the realm of possibility, and scientists continue to investigate whether the outer solar system might harbor habitable environments. The human exploration of the outer solar system has been conducted entirely through robotic spacecraft. No human has ventured beyond the Moon, and the distances involved make human exploration of the outer solar system impractical with current technology. However, robotic spacecraft have provided invaluable insights into the outer solar system. Voyager 1 and Voyager 2, launched in 1977, have become humanity's ambassadors to the outer solar system and beyond. These remarkable spacecraft conducted close-up studies of Jupiter, Saturn, Uranus, and Neptune, and both continue to function today, transmitting data from the edge of the solar system, in the region where the solar wind transitions to the interstellar medium. The Voyager spacecraft represents some of humanity's greatest achievements. Voyager 1, launched toward Jupiter and Saturn, subsequently visited Uranus and Neptune before being flung outward into the depths of space by a gravitational assist from Neptune. Voyager 2 followed a similar path. Both spacecraft have now entered interstellar space, the region beyond the heliopause, and both continue to transmit data back to Earth. The signals from these spacecraft take over 20 hours to reach Earth, traveling at the speed of light across distances that stagger the human imagination. The fact that these spacecraft, launched before many people reading this were born, continue to function and transmit data is a testament to the brilliance of their design and the dedication of the teams that continue to operate them. The messages carried aboard the Voyager spacecraft are particularly poignant. Each spacecraft carries a golden record containing images, sounds, and music from Earth, a time capsule meant for any civilization that might encounter the Voyager spacecraft millions of years in the future. The record includes greetings in 55 languages, music from cultures around the world, and scientific diagrams. It is humanity's message to the cosmos, a statement of who we are and where we come from. In this way, the Voyager spacecraft are not merely scientific instruments but also symbols of humanity's curiosity and our desire to reach out into the universe and make contact with whatever might exist out there. Other spacecraft have also explored the outer solar system. The New Horizons spacecraft, launched in 2006, conducted a spectacular flyby of Pluto in July 2015, sending back the first close-up images of this distant world. The images revealed a world of stunning complexity, with mountains of water ice towering kilometers high, vast plains of frozen nitrogen, and intricate canyons carved into the surface. The discovery that Pluto possesses such geological complexity was surprising to many scientists, who had expected a simple, geologically dead world. Instead, Pluto proved to be a geologically active body, with evidence of internal heat and possible cryovolcanism, the eruption of water and other frozen volatiles rather than molten rock. Following its encounter with Pluto, New Horizons continued onward to study other objects in the Kuiper Belt. In January 2019, it conducted a close approach to a small Kuiper Belt object designated MU-69, which has since been named Arrokoth. Images from this encounter revealed a fascinating contact binary object, two distinct bodies orbiting each other in close proximity, likely held together by weak gravity. The shape of Arrokoth has been compared to a cosmic snowman or a peanut, and its structure suggests that it formed through a gentle collision between two smaller objects billions of years ago, a process believed to be important in the formation of larger bodies in the outer solar system. The discoveries made by spacecraft exploring the outer solar system have revolutionized our understanding of these distant regions. They have revealed worlds of unexpected complexity and beauty, challenging our preconceptions and inspiring us to continue exploring. Yet even with all we have learned, the outer solar system remains largely mysterious. The vast majority of objects in the Kuiper Belt and Oort Cloud have never been directly observed. Our knowledge is based on the study of relatively nearby objects and on theoretical models of how the solar system formed and evolved. As technology advances and new telescopes and spacecraft are developed, our understanding will continue to improve. Looking toward the future, several missions have been proposed to explore the outer solar system more thoroughly. Some proposals involve sending spacecraft to the Oort Cloud or to conduct more detailed studies of Kuiper Belt objects. One ambitious proposal involves sending a spacecraft on a high-speed trajectory that would allow it to reach the nearest stars within a few decades, thereby providing humanity with our first close-up views of stellar systems other than our own. Such missions remain in the realm of speculation for now, limited by our current technological capabilities and the enormous distances involved. However, the history of space exploration shows that what seems impossible today often becomes routine in the future. The existence of the Kuiper Belt, the Oort Cloud, and the vast expanse of the outer solar system transforms our understanding of what the solar system is. It is not a compact system dominated by 8 planets and a few asteroids. Rather, it is a vast realm extending from the Sun across distances that take light years to measure, populated by countless icy bodies, and extending far into the darkness. Our solar system is not an isolated island in space but rather a complex system that gradually transitions into the interstellar medium, with no clear boundary between what is solar and what is interstellar. This understanding also places Earth and humanity in perspective. Our planet orbits a medium-sized star in the outer regions of a spiral galaxy, a star that is surrounded by an enormous cloud of icy bodies. We exist in an incredibly privileged position, in the habitable zone of our star, where conditions are just right for life as we know it to flourish. Yet this privileged position is fragile, and the outer solar system reminds us of the cosmic forces that shape and sometimes threaten our world. The Kuiper Belt and Oort Cloud are sources of comets that have occasionally struck Earth, causing catastrophic extinctions. They are repositories of material left over from the formation of our planetary system. They are the outposts of the Sun's domain, the frontier of the solar realm. As we look outward at the outer solar system, we are looking back in time. The objects we observe there, particularly in the Oort Cloud, are largely unchanged since the formation of the solar system, cosmic fossils preserving the conditions and characteristics of the early solar nebula. By studying these distant objects, we are studying the history of our own world and the processes that led to its formation. We are reading the pages of a cosmic history book written in ice and rock, billions of kilometers from our home. This is the significance of the outer solar system. It is not merely a distant, cold, and barren region beyond the planets we know. It is a window into our past, a frontier of exploration, and a reminder of the vast and complex cosmos in which we reside. The relationship between our solar system and the nearby interstellar environment is far more dynamic than it might initially appear. Our star does not sit motionless in space. Rather, the entire solar system moves through the galaxy in a complex trajectory, completing one orbit around the galactic center approximately every 250 million years. This motion has profound consequences for the stability of the outer solar system and for our understanding of past cosmic events. As the Sun moves through the galactic disk, it occasionally encounters other stars, and these encounters can have significant effects on the Oort Cloud. When a star passes relatively close to our solar system, and by cosmic standards, relatively close, might mean within a light year or two, the gravitational pull of that passing star can perturb objects in the Oort Cloud, knocking them from their stable orbits. Some of these perturbed objects will be flung outward, into interstellar space, never to return. Others will be deflected inward, toward the inner solar system and the planets. This process, occurring sporadically throughout the history of the solar system, may explain the timing and frequency of large comet impacts on Earth and the other terrestrial planets. This mechanism has been proposed as an explanation for certain extinction events in Earth's biological history. While the extinction of the dinosaurs was definitively caused by an asteroid impact, other extinctions may have been caused by the effects of increased cometary activity in the inner solar system. If a nearby star passage disturbed the Oort Cloud, triggering a shower of comets over thousands or millions of years, the cumulative effects of multiple impacts, even if individually smaller than the dinosaur killer asteroid, could cause significant environmental disruption and species extinctions. Whether this has actually occurred remains a subject of active research and debate among planetary scientists. Beyond the question of stellar encounters, the outer solar system is also shaped by its own internal dynamics. Objects in the Oort Cloud are not static. They orbit the Sun in highly elliptical orbits that can be inclined at virtually any angle to the plane of the planets. The gravitational interactions between these objects, though individually very weak given their enormous separations, can accumulate over millions of years to produce measurable changes in orbital elements. Additionally, encounters between objects in the Oort Cloud can occur, and while such collisions are extraordinarily rare given the vast distances involved, they do happen from time to time. When they do, they can produce fragments and alter trajectories in ways that might eventually send an object inward toward the inner solar system. The chemical composition of objects in the outer solar system provides crucial information about the early solar system environment. The most primitive meteorites that fall to Earth today are thought to come from the asteroid belt, or from small bodies in the inner solar system, and they preserve records of the chemical conditions that existed in the solar nebula 4.5 billion years ago. Spectroscopic observations of distant Kuiper Belt objects, while limited by their great distance, suggest that their compositions are generally consistent with models of the early solar nebula. The presence of water ice, methane ice, ammonia ice, and various rocky minerals in the outer solar system indicates that these materials were present in the solar nebula and accreted into the bodies we observe today. One of the most intriguing discoveries in recent years has been the detection of organic molecules in meteorites and in the outer reaches of the solar system. Organic molecules, compounds based on carbon that are the chemical foundation of life, have been detected in meteorites, in the atmospheres of comets, and in dust from the outer solar system. These discoveries have led some scientists to propose that the building blocks of life may have originated in the outer solar system, or even in interstellar space. Delivered to Earth by comets and meteorites. This hypothesis, sometimes referred to as panspermia or exogenesis, suggests that life or its precursors may have origins beyond Earth. While the idea remains controversial, the discovery of organic compounds throughout the solar system certainly shows that the chemistry of life is not unique to Earth but is present throughout the cosmos. The role of the outer solar system in delivering water to the inner planets is another area of active research. The abundance of water on Earth is one of the great mysteries of planetary science. Where did all this water come from? The young Earth, forming in the warm inner solar system, would not have been a natural place for large quantities of water to accumulate. Instead, scientists increasingly believe that much of Earth's water was delivered by impacts from icy bodies originating in the outer solar system. During the late heavy bombardment, a period of intense asteroid and comet impacts occurring roughly 3.5 to 4 billion years ago, Earth and the other terrestrial planets were struck by numerous large bodies. Many of these bodies likely originated in the outer solar system, in the Kuiper Belt or beyond, and carried with them enormous quantities of water ice. As these objects impacted Earth, the heat of impact melted the ice, and the water became part of our planet's inventory of volatiles, eventually becoming our oceans, atmosphere, and the basis for the emergence of life. This scenario highlights the intimate connection between the outer solar system and the development of life on Earth. Without the Kuiper Belt and the objects it contains, Earth might be a dry, lifeless world. The water that enables life as we know it may be a gift from the cold, dark regions of the outer solar system, delivered by cosmic messengers billions of years ago. This connection reminds us that the distant, seemingly irrelevant outer solar system is actually fundamental to our own existence. The question of what lies at the absolute boundary of the solar system, the heliopause and the region beyond, is currently being addressed by the Voyager spacecraft. Voyager 1, which crossed the heliopause in 2012, has provided scientists with unprecedented data about the transition from the heliosphere to interstellar space. The instruments aboard Voyager 1 detected a sharp increase in cosmic ray intensity at the heliopause, indicating the transition to an environment more heavily bombarded by galactic cosmic rays. The spacecraft also detected a change in the direction of the local interstellar magnetic field, which becomes more prominent once the protective influence of the solar wind diminishes. The data from Voyager 1 has revealed that the boundary between the solar system and interstellar space is more complex than previously anticipated. Rather than a simple transition, there appears to be a structured boundary region with distinct layers and zones. Just inside the heliopause, the solar wind is slowed by interaction with the interstellar medium, creating a shock wave called the termination shock. Beyond this, in the region between the termination shock and the heliopause, the solar wind is deflected and compressed. At the heliopause itself, the pressure of the solar wind balances the pressure of the interstellar medium. Beyond the heliopause lies the local interstellar medium, a region characterized by lower temperature, higher cosmic ray flux, and a different magnetic field configuration than the heliosphere. The local interstellar medium, the region of space immediately surrounding our solar system, is not a simple vacuum. It contains clouds of neutral hydrogen and helium, dust particles, and a weak magnetic field. The temperature of this medium is roughly 6,000 to 10,000 Kelvin, far colder than the interior of the heliosphere but warmer than the depths of the Oort Cloud. The density of material is extraordinarily low by terrestrial standards. The number of atoms per cubic centimeter is roughly 1/10 that of the most perfect laboratory vacuum that can be achieved on Earth. Yet this material, when distributed across enormous volumes of space, represents a significant amount of matter. One of the most remarkable discoveries in recent years has been the detection of a region called the local bubble, a sphere of interstellar space roughly 1,000 light-years in diameter, within which our solar system resides, characterized by an unusually low density of interstellar gas and dust. The exact origin of the local bubble is uncertain, but it is thought to have been created by one or more supernova explosions that occurred in the neighborhood of our solar system millions of years ago. These explosions would have blown away the surrounding gas and dust, creating the low-density region we observe today. The boundaries of the local bubble are marked by walls of denser material where the expanding debris from the supernovae has compressed the surrounding interstellar medium. The existence of the local bubble has important implications for the history of the solar system. The low density of interstellar material within the local bubble means that the solar system has experienced a relatively benign interstellar environment for millions of years. If the solar system were instead embedded in a denser molecular cloud, The interaction with interstellar material could cause significant perturbations to the Oort Cloud and potentially increase the flux of comets into the inner solar system. The fact that we live in a relatively low-density region of space has been somewhat fortuitous for the stability of the solar system, and by extension, for the continuation of life on Earth. However, the local bubble is not static. It is slowly expanding, and the boundaries are gradually shifting. Eventually, over millions of years, the solar system may migrate out of the local bubble and into denser regions of interstellar space. When this occurs, the increased density of the surrounding medium could have noticeable effects on the Oort cloud and the flux of comets entering the inner solar system. Some scientists have speculated that such transitions from low-density to high-density interstellar regions might be correlated with periods of increased cometary bombardment, and potentially, with extinction events on Earth. The interface between the solar system and the interstellar medium is also significant for our understanding of cosmic rays. Cosmic rays are high-energy particles, primarily protons and atomic nuclei, that originate from sources throughout the galaxy. These particles travel at speeds close to the speed of light and possess enormous amounts of energy. When cosmic rays encounter the magnetic field of the solar system and the solar wind, many of them are deflected and prevented from reaching the inner solar system. This shielding effect reduces the flux of cosmic rays in the inner solar system compared to interstellar space. The strength of this shielding depends on the strength of the solar magnetic field and the intensity of the solar wind, both of which vary with the solar cycle and over longer timescales. The shielding of Earth from cosmic rays by the solar system's magnetic field and the solar wind is significant for life on Earth. Cosmic rays can damage DNA and cause mutations in living organisms. Earth's magnetic field provides an additional layer of shielding, deflecting many cosmic rays away from the surface. The combination of these two shielding mechanisms, one from the solar system and one from Earth itself, protects surface-dwelling life from the worst effects of cosmic radiation. If this shielding were to be significantly weakened, such as might occur during periods of reduced solar activity or solar magnetic field strength, the increased cosmic ray flux could have biological consequences for life on Earth. The structure of the outer solar system, as we understand it today, is the result of billions of years of orbital evolution and gravitational interactions. The current distribution of objects in the Kuiper Belt and Oort Cloud is not necessarily identical to the distribution at the time of the solar system's formation. Instead, it reflects the outcome of a long history of dynamical processes. Objects have been ejected, perturbed, and rearranged. Some objects that originated elsewhere in the solar system may have been scattered into the outer regions, while some objects that originally formed in the outer regions may have been scattered inward or outward. This dynamical history is recorded, to some extent, in the orbital characteristics of objects in the outer solar system. Objects with unusual orbital inclinations or with orbital characteristics that seem inconsistent with simple formation in their current locations provide clues about past dynamical events. The recently discovered object nicknamed Planet 9, for instance, if confirmed to exist, would possess an orbital configuration that is difficult to explain through standard planetary formation and migration models. Its existence would suggest that additional dynamical processes occurred in the outer solar system beyond those currently accounted for in most theoretical models. The search for Planet 9 continues, with astronomers using various observational techniques to attempt to detect this elusive object. The exploration and study of the outer solar system will continue to be a priority for astronomical research. New ground-based telescopes and space-based observatories are being developed that will allow for more sensitive observations of distant, faint objects. Spectroscopic studies will provide information about the chemical composition of Kuiper Belt objects and other distant bodies. Continued observations of the Voyager spacecraft will provide data about the nature of interstellar space and the heliosphere boundary. Future space missions may visit additional Kuiper Belt objects or conduct studies of the Oort Cloud, though the practical challenges involved in reaching objects at such distances are immense. The significance of the outer solar system extends beyond its scientific interest. The outer solar system represents a frontier of human knowledge, a region about which we are still learning fundamental facts. It represents the domain of our star, the region of space in which the sun's gravity, though vastly weakened, still exerts control over objects orbiting within it. It is a region of cosmic history, preserving in its current configuration evidence of events that shaped the formation of our planetary system. It is a reminder of the vast scale of the universe and our tiny place within it. And it is, potentially, a region of habitable worlds, places where conditions might exist for forms of life fundamentally different from anything known on Earth. When we contemplate the outer solar system, we are contemplating more than just rocks and ice orbiting at great distances. We are contemplating the history of our world, the origins of the material that makes up our planet and ourselves, the processes by which planetary systems form and evolve, and our place in the cosmos. The outer solar system is not merely a destination for future exploration, it is a key to understanding the universe itself and our role within it. In studying the Kuiper Belt and the Oort Cloud, in tracking comets and analyzing meteorites, in launching spacecraft to the edge of interstellar space, we are engaging in one of humanity's most profound endeavors, the quest to understand our origins and our cosmic context. The discovery of exoplanets has transformed our perspective on the outer solar system from a unique phenomenon into an example of a universal pattern. Since the first confirmed detection of an exoplanet orbiting a Sun-like star in 1995, astronomers have identified thousands of planetary systems around other stars. Many of these systems exhibit structures that bear striking similarities to our own solar system, with evidence suggesting that circumstellar disks of icy bodies are common features around mature stars. This comparative approach has revolutionized planetary science, allowing us to test theories developed from studying our solar system against data from dozens or hundreds of other systems. Some exoplanetary systems show evidence of debris disks, regions of dust, and small bodies analogous to the asteroid belt or Kuiper Belt of our solar system. These debris disks are often detected through infrared observations, as dust particles in these regions absorb starlight and re-emit it at infrared wavelengths. The structure and composition of these debris disks provide insights into the formation and evolution of those planetary systems. In many cases, the presence of a debris disk is interpreted as evidence that planets exist in the system, as planetary gravity is responsible for sculpting and maintaining the disk structure. The fact that debris disks are common around nearby stars suggests that the outer regions of planetary systems are universal features, not peculiarities unique to our solar system. Several exoplanetary systems have been found to possess large outer planets in configurations similar to Jupiter and Saturn. One particularly interesting example is the Tau Ceti system, located approximately 11.9 light-years from Earth, which may harbor multiple super-Earths and possibly terrestrial planets in a stable configuration. Another well-studied system is the Kepler-90 system, which contains 8 known planets, making it tied with our solar system for the most planets detected in a single system. The existence of other multi-planet systems demonstrates that the architecture of our solar system, once thought to be somewhat unusual, is actually an example of a relatively common outcome of planetary formation. The study of exoplanetary systems has also revealed that planetary architectures can be far more diverse than those found in our solar system. Some systems contain hot Jupiters, massive gas giant planets orbiting extremely close to their parent stars in configurations that would be impossible in our solar system. Other systems contain planets orbiting in highly eccentric, elongated orbits, vastly different from the nearly circular orbits of the planets in our solar system. Still other systems contain planets in very close orbital proximity to one another, sometimes only slightly separated. These diverse architectures are thought to result from different planetary migration histories and different initial configurations of planetary systems. They remind us that while our solar system follows one particular pattern, many other patterns are possible and apparently common in the universe. The potential habitability of exoplanets, particularly those in the habitable zones of their parent stars, where conditions might allow for liquid water to exist on planetary surfaces, has become a major focus of exoplanet research. Dozens of potentially habitable exoplanets have been identified, and future space telescopes will be capable of analyzing the atmospheres of these distant worlds, potentially detecting atmospheric signatures of biological processes. While we have not yet found definitive evidence of life beyond Earth, the discovery of potentially habitable worlds orbiting distant stars suggests that the conditions necessary for life may be widespread throughout the galaxy. By extension, if habitable planets are common, then life itself may be a common phenomenon in the universe, and we may not be unique in our corner of the cosmos. The possibility of life in the outer regions of planetary systems has gained attention in recent years. Some researchers have speculated that habitable environments might exist within or beneath the icy crusts of moons or small bodies in the outer regions of planetary systems, analogous to proposed habitable environments beneath the icy surfaces of Saturn's moon Enceladus or Jupiter's moon Europa. If such environments exist around distant stars, they might harbor life fundamentally different from anything on Earth. This possibility expands the definition of the habitable zone and suggests that the outer regions of planetary systems, once dismissed as barren wastelands, might actually be repositories of extraterrestrial life. Returning to our own solar system, the study of icy bodies has revealed surprising complexity and geological activity. The moons of the outer planets, particularly Saturn's Enceladus and Jupiter's Europa, have emerged as prime targets in the search for life within our solar system. Both moons possess subsurface oceans of liquid water, maintained in liquid form by tidal heating from their parent planets. The water in these oceans is in contact with rocky material, potentially providing the chemical energy and nutrients necessary to support microbial life. Missions to Enceladus have detected organic compounds in the plumes of water vapor that erupt from the moon's south polar region, suggesting that complex chemistry is occurring in the subsurface ocean. The discovery of these potentially habitable environments has led many scientists to view the outer solar system as perhaps the most promising location for the discovery of extraterrestrial life within our planetary system. The geology of bodies in the Kuiper Belt and outer solar system differs markedly from the geology of terrestrial bodies in the inner solar system. In the inner solar system, geological processes are dominated by heat, whether from planetary interiors, from impacts, or from radiation. In the outer solar system, at temperatures near absolute zero, geological processes are dominated by ice. Cryovolcanism, the eruption of water and other frozen volatiles, represents the dominant mode of volcanism on icy bodies. Cracks form in icy crusts, allowing subsurface material to well up and freeze on the surface. Over billions of years, such processes can reshape the surfaces of icy worlds. The discovery that Pluto exhibits evidence of cryovolcanism, demonstrated by the New Horizons spacecraft, was startling to many scientists and demonstrated that even at the remote margins of the solar system, geological activity can occur. The color and reflectivity properties of bodies in the Kuiper Belt provide clues about their surface composition. Many Kuiper Belt objects are quite dark, with reflectivities, the fraction of sunlight they reflect, of only 10 to 30%, comparable to coal or worn asphalt. This darkness is thought to result from the accumulation of organic compounds and other dark materials on the surface, produced by the chemical alteration of ices and other compounds by cosmic rays and ultraviolet radiation from the distant sun. Some bodies are brighter, with reflectivities of 50% or more, suggesting surfaces of relatively pure water ice. The variation in surface properties among Kuiper Belt objects suggests that these bodies have diverse histories and compositions, having been subject to different amounts of irradiation and cosmic ray exposure. The rotation rates and spin orientations of Kuiper Belt objects provide additional information about their histories. Some objects rotate relatively slowly, completing one rotation over many hours or even days. Others rotate rapidly, completing a rotation in mere hours. The rotation rates are thought to result from collisions and gravitational interactions that have occurred over billions of years. Additionally, the spin axes of some objects point in unexpected directions, suggesting that these objects have been knocked sideways by collisions or gravitational interactions. By studying the rotational properties of Kuiper Belt objects, astronomers can infer something about the collision and dynamical histories of these bodies. The search for new objects in the Kuiper Belt and outer solar system continues using advanced observational techniques. Ground-based surveys employing large telescopes equipped with sensitive detectors have discovered many previously unknown objects. These surveys scan large areas of sky at regular intervals, looking for the characteristic motion of objects at great distances from the Sun. Space-based telescopes offer advantages in terms of freedom from atmospheric distortion and the ability to detect fainter objects, though they cover smaller areas of sky than ground-based surveys. As survey sensitivity improves, we discover smaller and smaller objects, gradually filling in our census of the outer solar system's population. One particularly important tool for discovering and characterizing outer solar system objects is the technique of occultation, wherein a distant object passes in front of a star, causing the star's light to dim briefly. By observing the time and intensity of this dimming, astronomers can infer the size and shape of the occulting object. Occultation observations of Pluto, conducted from the ground, provided accurate measurements of Pluto's diameter before the New Horizons spacecraft ever arrived at Pluto. In recent years, occultation observations have been used to characterize numerous small Kuiper Belt objects, providing detailed information about their sizes and shapes. The dynamics of the Kuiper Belt itself is an area of intense research. The gravitational interactions between objects in the Kuiper Belt can cause orbits to evolve over time. Additionally, the gravitational influence of the giant planets, particularly Neptune, plays a crucial role in shaping the structure of the Kuiper Belt. The so-called NICE model, named after the French city where it was developed, proposes that the outer planets underwent significant migration in the early history of the solar system, triggered by gravitational interactions with the planetesimal disk. According to this model, during the first few 100 million years of the solar system's existence, the giant planets rearranged themselves into a new configuration, scattering planetesimals throughout the outer solar system in the process. This model successfully explains many observed features of the solar system, including the current orbital configurations of the planets and the structure of the Kuiper Belt. The NICE model predicts that during the period of giant planet migration, the inner solar system would have experienced a catastrophic bombardment as the scattered planetesimals were flung inward. Evidence for this late heavy bombardment is found in the lunar sample record. Moon rocks brought back by the Apollo missions show evidence of a spike in crater-forming impacts roughly 4 billion years ago. This bombardment would have had profound consequences for the early Earth, potentially delivering vast quantities of water and organic compounds, but also causing immense destruction. The emergence of life on Earth appears to have occurred despite, or perhaps even because of, this bombardment, with life possibly originating in the warm, protected environments of hydrothermal vents on the ocean floor, shielded from the worst effects of impact-induced surface sterilization. The concept of planetary habitability, the conditions necessary for a world to support life, has expanded considerably with our understanding of the outer solar system and exoplanetary systems. For much of the 20th century, habitability was thought to require a planet in the habitable zone of a star, where temperatures would allow liquid water to exist on the surface. However, the discovery of hydrothermal vent communities on Earth, existing in the deep ocean in total darkness and deriving energy from chemical reactions rather than sunlight, expanded our conception of habitable environments. Combined with evidence for subsurface oceans on icy moons, this has led to the concept of a larger, habitable zone, one that extends beyond simple surface habitability to include any environment where liquid water, chemical energy, and appropriate elemental composition exist. The moons of the outer solar system represent a diverse array of bodies with varied geological histories. Beyond Europa and Enceladus, other moons possess features of scientific interest. Titan, the largest moon of Saturn, possesses a thick atmosphere and liquid hydrocarbon lakes near its poles, making it a unique body within the solar system. Io, a moon of Jupiter, is geologically the most active body in the solar system, with numerous active volcanoes. Miranda, a moon of Uranus, displays a tortured surface suggesting a violent collision history. Triton, the largest moon of Neptune, rotates backward relative to Neptune's rotation, indicating that it was likely captured from the Kuiper Belt at some point in the past. Each of these moons tells a story of cosmic evolution and geological processes. The history of the discovery of the outer solar system reflects the progressive expansion of human knowledge and observational capability. Until the development of the telescope in the early 1700s, only the 5 inner planets and the Sun and Moon were known to humanity. The discovery of Uranus in 1781 doubled the known extent of the planetary system. Neptune was discovered in 1846 through a combination of observation and mathematical prediction. Pluto was discovered in 1930 through painstaking photographic survey. The Kuiper Belt was not confirmed to exist until the 1990s, despite having been predicted decades earlier. This pattern of prediction followed by eventual observation continues today, with scientists predicting the existence of objects and phenomena in the outer solar system that are subsequently confirmed through improved observational techniques. The technological requirements for studying the outer solar system are considerable. Because objects in the Kuiper Belt and Oort Cloud are so distant and so small, they reflect very little sunlight and are difficult to detect. Ground-based telescopes must be extremely large and sensitive to detect these faint objects. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, is a facility currently being completed that will revolutionize the study of the outer solar system through its combination of large aperture, wide field of view, and rapid survey capability. This telescope will be capable of discovering faint, distant objects systematically, potentially discovering thousands of new outer solar system bodies over its operational lifetime. Space-based observatories also play a crucial role in studying the outer solar system. The James Webb Space Telescope, launched in 2021, possesses unprecedented infrared sensitivity and will be capable of detecting very distant and faint objects. Future missions may include dedicated spacecraft designed to conduct infrared surveys of the outer solar system from space, where the absence of atmospheric interference allows for optimal sensitivity. Some proposed missions involve sending spacecraft to conduct close-up observations of Kuiper Belt objects, similar to the New Horizons mission. Such missions face enormous challenges given the distances involved, but they would provide invaluable scientific data. The question of whether life might exist in the outer solar system is one of the most profound questions in planetary science today. While the conditions in the outer solar system are harsh by terrestrial standards, with temperatures near absolute zero and virtually no sunlight, life on Earth has demonstrated remarkable adaptability. Extremophile organisms on Earth exist in environments previously thought incompatible with life, such as deep-sea hydrothermal vents, hot springs, subsurface rocks kilometers below the surface, and even within the nuclear reactor at Chernobyl. If life can flourish in such extreme environments on Earth, it is not unreasonable to wonder whether life might exist in the equally extreme environments of the outer solar system. The chemical requirements for life, as currently understood, are relatively modest: liquid water, carbon and other essential elements, and a source of energy. All of these are present in various forms throughout the outer solar system. Liquid water exists, or may exist beneath icy surfaces of moons and possibly within Kuiper Belt objects. Carbon and other elements are present in the rocky and icy bodies of the outer solar system. Sources of energy include tidal heating from orbital interactions, radioactive decay within planetary bodies, and chemical reactions between water and rock. If the chemical requirements for life are indeed met somewhere in the outer solar system, the possibility of life existing there cannot be dismissed. The detection of life in the outer solar system, if it exists, would be one of the most profound discoveries in human history. It would demonstrate that life is not unique to Earth, that the origin of life is not an extraordinarily rare event, and that life may be widespread throughout the universe. The search for life in the outer solar system is thus not merely a scientific curiosity but an endeavor of immense philosophical significance. It addresses fundamental questions about the nature of life, the nature of the universe, and our place within it. As we continue to explore and study the outer solar system, we expand our understanding of the cosmos and our place within it. We discover that the region beyond Neptune is not a barren wasteland but a realm of great complexity and scientific interest. We find that the outer solar system holds keys to understanding how planetary systems form and evolve, how life may have originated on Earth, and where life might exist elsewhere. We recognize that the outer solar system is intimately connected to our own existence, having provided the water and organic compounds that make up our planet and ourselves. In studying the outer solar system, we are studying ourselves, our origins, and our cosmic heritage. The atmospheric composition of bodies in the outer solar system reveals important chemical information about the early solar nebula and the processes that have occurred since these bodies formed. Many small bodies in the Kuiper Belt possess thin atmospheres or show evidence of outgassing, where volatile materials escape from the surface into space. These atmospheres are ephemeral, lasting only while the bodies remain at certain distances from the Sun or during specific seasonal variations in their orbits. During the close approaches of cometary bodies to the Sun, the heating can trigger the sublimation of surface ices, creating temporary atmospheres that expand and eventually dissipate as the comet moves back into the cold depths of space. The spectroscopic analysis of these atmospheres has revealed the presence of various molecular species, including water vapor, carbon dioxide, carbon monoxide, methane, and ammonia. The relative abundances of these molecules vary among different comets and outer solar system bodies, suggesting that they formed under different conditions or experienced different thermal and chemical processing over their history. Some bodies show evidence of complex organic molecules, including cyanides and other carbon-bearing compounds that are precursors to the chemistry of life. The detection of these compounds in cometary material has led researchers to propose that comets delivered not only water but also the chemical seeds of life to the early Earth. The interaction between the solar wind and the atmospheres of comets and icy bodies represents another important physical process. As the solar wind encounters the expanding atmosphere of a comet, it causes the charged particles in the comet's atmosphere to be deflected and accelerated. This creates the characteristic tail of a comet, which always points away from the Sun regardless of the comet's direction of motion. The interaction between the solar wind and cometary atmospheres is a form of plasma physics, the physics of ionized gases, and studying these interactions provides insights into plasma behavior that have applications beyond astronomy, including in plasma physics laboratories and in the study of stellar atmospheres. The thermal structure of bodies in the outer solar system is dominated by the extremely low temperatures and the slow rate of heat transfer. In the inner solar system, where bodies receive significant energy from the Sun, thermal gradients within planetary bodies create geological activity and drive atmospheric circulation. In the outer solar system, bodies receive so little solar energy that their temperatures are determined primarily by their thermal history and any internal heat sources, such as radioactive decay or tidal heating. Many icy bodies in the outer solar system are believed to have frozen solid billions of years ago and have changed little since. Others, particularly those in orbit around massive planets and experiencing tidal heating, remain geologically active despite the frigid external environment. The concept of tidal heating deserves deeper examination, as it is crucial to understanding the geology of bodies in the outer solar system. Tidal heating occurs when an object orbiting a massive body experiences gravitational forces that vary as the object moves closer to and farther from the primary body. These varying forces create stresses within the orbiting body that generate heat through frictional dissipation. The intensity of tidal heating depends on the mass of the primary body, the orbital distance and eccentricity of the satellite, and the internal structure and rigidity of the satellite itself. For massive objects orbiting close to gas giants like Jupiter and Saturn, tidal heating can be substantial, potentially providing more energy than that received from the Sun. Europa, the fourth largest moon of Jupiter, is a prime example of a body where tidal heating plays a crucial role. Europa's orbit around Jupiter is slightly elliptical, meaning that the moon experiences varying gravitational forces that deform it as it orbits. This deformation generates heat through tidal dissipation, and this heat is believed to maintain a subsurface ocean of liquid water despite Europa's location far from the Sun. Enceladus, similarly, experiences tidal heating from its orbit around Saturn, and this heating maintains the subsurface ocean that ejects plumes of water vapor and organic compounds into space. Without tidal heating, these moons would have frozen solid billions of years ago, and their subsurface oceans would never have formed or would have been lost long ago. The search for biosignatures in the outer solar system represents one of the most challenging but potentially rewarding endeavors in astrobiology. Biosignatures are indicators of the presence of life, which might include certain chemical compounds produced by biological processes, morphological structures indicative of biological activity, or patterns in atmospheric composition that are difficult to explain through non-biological processes. On Earth, oxygen in the atmosphere is a strong biosignature, as oxygen is produced in large quantities by photosynthetic life and is rapidly oxidized in the absence of continuous biological production. Other potential biosignatures include methane in an exoplanet's atmosphere, certain isotopic ratios in organic compounds, or the presence of complex organic molecules in unexpected environments. In the outer solar system, the detection of biosignatures is considerably more difficult than on potentially habitable exoplanets. The extreme distances involved and the sparse nature of potentially habitable environments make direct detection challenging. Future missions to Europa or Enceladus might attempt to detect biosignatures by analyzing the composition of the subsurface oceans or their exiting plumes. Such a detection would be revolutionary, providing the first definitive evidence of life beyond Earth and demonstrating that life is not unique to our planet. However, the absence of detected biosignatures would not necessarily indicate the absence of life. It might merely reflect the limitations of our detection capabilities. The role of impact cratering in the outer solar system deserves consideration. While impacts are far less common at great distances from the Sun, they do occur. The small sizes and relatively low orbital velocities of bodies in the Kuiper Belt mean that impacts produce less energetic events than similar-sized bodies colliding in the inner solar system. Nevertheless, impacts can significantly alter the surfaces of icy bodies and can trigger geological processes such as cryovolcanism. The study of impact craters on outer solar system bodies provides information about the impact history of these worlds and can help estimate the current flux of impactors, the rate at which objects collide in these regions. The phenomenon of resonances in orbital mechanics plays a crucial role in structuring the outer solar system. A resonance occurs when two orbiting bodies have orbital periods that are related by a simple integer ratio. For example, if one object completes 2 orbits for every 3 orbits of another object, they are in a 2-to-3 resonance. Such resonances can trap orbits in stable configurations or, conversely, can create unstable regions where objects are unlikely to have stable orbits. The architecture of the Kuiper Belt shows clear evidence of resonances with Neptune, and these resonances have shaped the distribution of objects within the belt. Many Kuiper Belt objects are trapped in resonances with Neptune, while regions between resonances are relatively empty, having been cleared of objects through gravitational scattering. The classical Kuiper Belt, the region of the belt populated by objects with relatively circular, low-inclination orbits similar to the orbits of the planets, is distinct from the scattered disk, a region extending farther from the Sun and containing objects with more elliptical and highly inclined orbits. The distinction between these two regions reflects different formation mechanisms and histories. The classical Kuiper Belt is thought to have formed in its current location through the accretion of planetesimals in a disk around the young Sun. The scattered disk, by contrast, is thought to consist largely of objects that were scattered from their original formation locations by gravitational interactions with the giant planets during the period of planetary migration. The dwarf planet Eris, which resides in the scattered disk, has been a subject of particular interest. Eris's high orbital inclination and eccentricity suggest a violent history of gravitational interactions. Its discovery in 2005 by a team led by Mike Brown at Caltech was a pivotal moment in planetary science, as it provided the impetus for the redefinition of planetary categories. Eris is about 27% more massive than Pluto, though slightly smaller in diameter, indicating a higher density, possibly reflecting a composition richer in rock relative to ice compared to Pluto. The study of Eris and other scattered disk objects provides insights into the dynamical processes that shaped the outer solar system billions of years ago. The concept of planetary migration, introduced earlier but deserving of deeper examination, has become central to modern understanding of planetary system formation. According to current models, giant planets do not form where we currently observe them. Instead, they form in a planetesimal disk closer to the central star and subsequently migrate to their current positions through gravitational interactions with the planetesimal disk. Jupiter may have formed at a distance of several astronomical units and then migrated, both inward and outward, over the course of millions of years. Saturn, Uranus, and Neptune similarly underwent migration. These migrations fundamentally reshaped the inner solar system, scattering planetesimals, establishing the current orbital configurations of the planets, and creating the Kuiper Belt as we observe it today. The primordial asteroid belt would have been far more massive than the current asteroid belt, containing as much material as a terrestrial planet. Most of this material was ejected from the inner solar system by gravitational interactions with the migrating giant planets, scattered into the outer solar system, or accreted into the giant planets themselves. A smaller fraction was scattered into the inner solar system, causing the late heavy bombardment that shaped the surfaces of the terrestrial planets and possibly delivered water and organic compounds to Earth. Only a small residue of the original asteroid belt remains today, the bodies we observe in the current asteroid belt between Mars and Jupiter. The study of meteorites provides direct evidence of the planetesimal population of the early solar system. Meteorites are fragments of asteroids and other bodies that fall to Earth, and they preserve a record of conditions in the early solar nebula. Primitive meteorites, such as carbonaceous chondrites, contain material that has changed little since the formation of the solar system 4.5 billion years ago. These meteorites contain water, organic compounds, and minerals that formed under conditions characteristic of the outer solar system, even though these meteorites are now found on Earth. The presence of these materials in meteorites indicates that material from the outer solar system was transported inward, consistent with models of planetary migration and the late heavy bombardment. The discovery of interstellar objects passing through the solar system represents a new frontier in observational astronomy. The first confirmed interstellar object, designated 1I/Oumuamua, was discovered in October 2017 as it passed through the inner solar system on a hyperbolic trajectory indicating that it originated from outside the solar system. Oumuamua's properties are mysterious. Its shape appears to be highly elongated, more like a cigar or pancake than the roughly spherical shape typical of solar system asteroids. Its color appears reddish, suggesting a composition rich in organic compounds. The object's trajectory showed evidence of non-gravitational acceleration, possibly resulting from outgassing as the object was warmed by solar heating. Though no visible outgassing or activity was observed, the implications of Oumuamua's discovery are profound. It demonstrates that the interstellar medium is populated with small bodies that occasionally pass through planetary systems. If similar objects pass through the solar system at measurable rates, then analogous objects must pass through other planetary systems as well. This raises the possibility that material and possibly microorganisms could be transported between planetary systems through the passage of interstellar objects. While panspermia, the transfer of life between worlds, remains a speculative concept, the existence of interstellar objects makes it at least physically possible for microorganisms to travel between stars. A second interstellar object, designated 2I/Borisov, was discovered in August 2019. Like Oumuamua, it was on a hyperbolic trajectory indicating origin from beyond the solar system. However, 2I/Borisov showed characteristics more typical of solar system comets, including a visible coma and tail. The discovery of 2I/Borisov confirmed that the passage of Oumuamua was not an anomaly but rather an example of a class of objects regularly entering the solar system from interstellar space. As survey capabilities improve, more interstellar objects are likely to be discovered, providing opportunities to study material from other stellar systems directly. The chemical composition of the interstellar medium surrounding our solar system provides context for understanding the outer solar system. The local interstellar medium consists primarily of neutral hydrogen and helium, with traces of heavier elements and dust particles. The presence of heavier elements reflects the fact that these elements are synthesized in stars and distributed into the interstellar medium through stellar explosions and other processes. The dust particles in the interstellar medium are composed of silicates, carbon, and other materials, and they serve as the seeds from which planets eventually form when stellar nurseries collapse to form new planetary systems. The influence of the galactic environment on the solar system extends beyond the occasional passage of nearby stars. The gravitational field of the Milky Way galaxy, though spread over enormous distances, still exerts a force on every object within the galaxy, including our solar system and the Oort Cloud. This galactic tide, the differential gravitational force across the solar system due to the galaxy as a whole, can perturb objects in the Oort Cloud, potentially triggering the infall of comets toward the inner solar system. The strength of the galactic tide varies as the solar system orbits the galactic center, and some scientists have speculated that the timing of extinction events on Earth might be correlated with the solar system's position in its galactic orbit. The eventual fate of the outer solar system is a subject of scientific speculation. If the Sun remains stable for its full lifetime of approximately 10 billion years, many of the processes currently active in the outer solar system will continue. However, on the timescale of trillions of years, dynamical effects will gradually eject objects from the solar system or cause them to spiral into the Sun. Eventually, after a timescale of roughly 100 trillion years, the solar system will be completely dispersed. Long before this, however, the Sun will exhaust its nuclear fuel and undergo transformation. In about 5 billion years, the Sun will enter its red giant phase, expanding to encompass the orbits of Mercury, Venus, and Earth. The outer solar system will remain relatively unaffected by this transformation, continuing to exist after the inner solar system has been consumed. After the red giant phase, the Sun will shed its outer layers, forming a planetary nebula, and eventually collapse into a white dwarf, a dense stellar remnant about the size of Earth but with the mass of the Sun. The Kuiper Belt and Oort Cloud will persist around this white dwarf, fundamentally unchanged except for the absence of solar radiation. This long-term perspective reminds us that the outer solar system, vast and unchanging as it appears on human timescales, is nevertheless subject to change and evolution on cosmic timescales. The dynamics of the outer solar system, the structure of the Kuiper Belt, and the population of the Oort Cloud are all products of the unique history of our planetary system, shaped by chance encounters with neighboring stars, by the migration of the giant planets, and by the countless gravitational interactions among billions of icy bodies. Understanding the outer solar system requires not only observation and measurement, but also imagination and patience, an appreciation for processes that unfold over billions of years and across billions of kilometers of space. It requires us to expand our conception of the solar system beyond the familiar planets and asteroids to encompass a far vaster realm, a realm that is no less magnificent and no less worthy of exploration and understanding than any other aspect of the cosmos. The stability of planetary orbits in our solar system over geological timescales is not guaranteed but rather the result of a delicate balance of gravitational forces. Computer simulations of the solar system have demonstrated that over sufficiently long timescales, millions to billions of years, the orbits of the planets can become chaotic, exhibiting unpredictable variations. While the inner planets remain relatively stable on timescales of hundreds of millions of years, over timescales approaching 1 billion years, small perturbations can accumulate, leading to significant changes in orbital elements. This chaos in the planetary system is not a flaw in our models but rather a reflection of a fundamental aspect of gravitational dynamics. Systems of more than two bodies can exhibit sensitive dependence on initial conditions, meaning that imperceptibly small differences in starting conditions can lead to vastly different outcomes over time. The outer solar system exerts a stabilizing influence on the inner planets through mechanisms that astronomers are still working to fully understand. The massive planets, particularly Jupiter and Saturn, act as gravitational anchors, their immense gravity helping to maintain the overall structure of the planetary system. Simultaneously, the Kuiper Belt and scattered disk, through their collective gravitational influence, provide a kind of counterbalance that helps stabilize planetary orbits. The removal or significant alteration of these outer structures could destabilize the inner planets. Conversely, had the outer planets formed in slightly different positions or with different masses, the entire architecture of the planetary system might be profoundly different, and the Earth's orbit might not be compatible with the existence of complex life. The transit method, a technique for detecting exoplanets through the dimming of starlight as a planet passes in front of its host star, has revealed much about the diversity of outer planetary systems. Many exoplanetary systems show evidence of planets with orbital periods measured in years or decades, indicative of planets in orbital regions analogous to our outer solar system. These planets orbit at distances from their host stars that correspond to regions where temperatures are too cold for rocky planets to retain volatile atmospheres but warm enough that complex chemistry can occur. The variety of planetary masses, orbital eccentricities, and orbital spacings observed in exoplanetary systems demonstrates that our solar system represents only one possible outcome of planetary formation and evolution. The concept of orbital resonances extends beyond simple two-body interactions to encompass complex multi-body phenomena. In some exoplanetary systems, chains of planets have been discovered in successive mean-motion resonances, where the orbital periods are related by simple integer ratios. These resonance chains are thought to form during the migration of planets through the protoplanetary disk and are subsequently preserved because they represent stable configurations. The Kepler-90 system, mentioned earlier, shows evidence of multiple resonances among its planets. The study of these systems provides insights into the final stages of planetary system assembly and the conditions that allow multiple planets to coexist in stable configurations. The infrared spectroscopy of dust and ice around other stars has revealed that dust and icy body populations similar to our Kuiper Belt are indeed common around main sequence stars of various types. The presence of warm dust in the inner regions of debris disks and cooler dust in outer regions suggests that debris disks have similar structural divisions to our solar system, with an active inner region and a colder outer region. The evolution of these debris disks over time can be tracked by observing systems at different ages. Young systems show more active and luminous debris disks, while older systems show fainter and more evolved disks. These observations provide a perspective on how our own solar system's Kuiper Belt may have evolved over its history. The detection of large quantities of carbon monoxide and other volatile molecules in the outer regions of some debris disks has surprised astronomers, as these molecules are expected to be quickly destroyed by ultraviolet radiation from the host star and by cosmic rays. The presence of these molecules suggests either that they are being continuously replenished through collisions among icy bodies or that they have only recently been released through impacts. This finding indicates that debris disks are not static, dead regions but rather dynamic places where ongoing geological and collisional processes occur. By analogy, our own Kuiper Belt may be more dynamic and active than was previously suspected. The search for Planet X, the hypothetical ninth planet beyond Neptune, has become one of the more intriguing mysteries in contemporary astronomy. Multiple independent lines of evidence suggest the presence of an undiscovered massive object in the outer solar system. The orbital elements of some extreme outer solar system objects, those with orbits extending to hundreds of astronomical units from the Sun, cluster in ways that are difficult to explain through statistical chance alone or through the known planet's gravitational influences. If a massive object with an orbital period of thousands of years and an orbital inclination significantly different from the plane of the planets existed in the outer solar system, it could gravitationally influence these extreme objects and produce the observed clustering of orbital elements. Several candidate locations for Planet 9 have been proposed, based on statistical analyses of the orbital distributions of known outer solar system objects. Some proposals place the planet at distances of several hundred astronomical units from the Sun, with an orbital period of between 500 and 20,000 years. If Planet 9 exists and is eventually discovered, it would represent a watershed moment in planetary science, demonstrating that the solar system contains at least one world that has remained undiscovered until the 21st century despite occupying a significant region of space. The discovery would also have implications for understanding planetary formation and migration, as such a massive object would have a profound effect on the structure and dynamics of the outer solar system. The question of whether Planet 9, if it exists, could be a captured rogue planet, a planet ejected from another stellar system and subsequently captured by the Sun's gravity, has been seriously considered by some researchers. The universe is believed to contain a vast population of rogue planets, ejected from their birth planetary systems through gravitational interactions. If such a rogue planet happened to pass close enough to our solar system, it could be captured into a highly elliptical orbit around the Sun. Such a planet would have an unusual orbit compared to planets that formed in situ around the Sun, and it would represent direct evidence of planetary immigration from an extrasolar origin. While the evidence for a captured rogue planet in our solar system remains speculative, the concept is not physically impossible and represents an intriguing possibility. The moon Triton, the largest satellite of Neptune, is believed to have originated as a Kuiper Belt object subsequently captured by Neptune's gravity. The evidence for this origin includes Triton's retrograde orbit, orbiting in the opposite direction to Neptune's rotation, and its compositional similarities to known Kuiper Belt objects. The capture of Triton would have been a violent event, generating immense heat through tidal interactions and gravitational dissipation. The current state of Triton, with its active cryovolcanism and young surface, may be evidence of ongoing tidal heating from an orbit that was recently circularized. Triton's capture demonstrates that large-scale migrations and captures of substantial bodies can occur in planetary systems, reminding us that the architecture of our solar system, while currently stable, is the product of a complex and sometimes violent history. The atmospheric escape from bodies in the outer solar system, the loss of atmospheric molecules into space, occurs even at these vast distances and frigid temperatures. The escape mechanism differs from that in the inner solar system. In the outer solar system, escape is primarily driven by cosmic rays and solar ultraviolet radiation ionizing atmospheric molecules and allowing them to escape the weak gravitational fields of small bodies. Additionally, the solar wind, though weak at these distances, can strip away atmospheric particles. Over billions of years, these processes can deplete the atmospheres of small bodies, though large bodies like planets retain atmospheres more effectively. This atmospheric escape represents a form of erosion, a wearing away of the volatile reservoirs of outer solar system bodies. The composition of cometary nuclei, as revealed through spacecraft encounters and remote observations, shows considerable diversity. Some comets appear to be relatively homogeneous mixtures of ice and dust, while others show evidence of compositional layering or heterogeneity, suggesting that different regions of a comet formed under different conditions or experienced different amounts of heating. The density of cometary nuclei is surprisingly low, typically less than one-half the density of water ice, indicating that comets are highly porous structures with significant void space. This porosity suggests that comets are aggregate structures, assemblies of smaller bodies that accreted together, rather than solid monolithic objects. The porosity may also explain why comets are so prone to fragmentation. They can break apart relatively easily when subjected to tidal stresses or impacts. The sublimation of cometary ices, the transformation of ice directly to gas as a comet approaches the Sun and is heated, is not a uniform process. Different ices sublime at different temperatures, so as a comet approaches the Sun and warms, the more volatile ices sublime first, followed by less volatile ices at greater solar distances. This differential sublimation can produce jets of gas and dust emerging from specific regions of the cometary surface, creating an asymmetric coma. The observation of such jets has provided information about the internal structure and composition of comets. Additionally, the differential sublimation can produce outgassing-induced accelerations that alter a comet's orbit, an effect known as the Yarkovsky effect or non-gravitational acceleration. The distribution of particle sizes in cometary dust, ranging from microscopic grains to larger aggregates, provides information about the fragmentation and aggregation processes that occur in the outer solar system. The smallest particles, often termed stardust, are the most interesting from a chemical perspective, as they can preserve complex organic molecules and other materials representative of conditions in the outer solar system. The collection of such particles by spacecraft, such as the Stardust mission to Comet Wild 2, provided samples of pristine cometary material that could be analyzed in laboratory settings. These analyses revealed the presence of amino acids and other organic compounds, confirming that the building blocks of life are indeed present in cometary material. The Oort Cloud's connection to nearby molecular clouds in the galaxy warrants consideration. Over the course of the solar system's orbit around the galactic center, it occasionally passes through regions of higher interstellar medium density, including molecular clouds that are sites of star formation. When the solar system enters such a region, the density of interstellar gas increases dramatically, exerting dynamical pressure on the Oort Cloud. This dynamical pressure could perturb Oort Cloud objects, and potentially trigger a shower of comets into the inner solar system. Some astronomers have proposed that the timing of extinction events on Earth coincides with the solar system's passages through dense interstellar clouds, though the evidence remains equivocal. The angular momentum budget of the solar system represents another constraint on models of planetary formation and evolution. The planets and Sun carry most of the angular momentum of the solar system, with Jupiter alone accounting for a substantial fraction. The planetesimals and objects in the Kuiper Belt carry a relatively small fraction of the total angular momentum. This angular momentum distribution is thought to result from the formation and evolution processes that shape the solar system. Planets that are more massive and orbit farther from the Sun carry more angular momentum than smaller, inner planets. Understanding how the planets acquired their current orbital angular momentum provides constraints on models of planetary migration and the dynamical rearrangement of the early solar system. The possibility of undiscovered moons orbiting bodies in the outer solar system remains significant. Many small bodies in the Kuiper Belt may possess satellites that have not yet been detected due to observational limitations. The discovery of such moons would provide information about binary formation processes in the outer solar system and would potentially reveal planetary systems in miniature, with the mass ratios between primary and satellite bodies serving as analogs for planetary systems. Additionally, the detection of moons around Kuiper Belt objects would provide targets for future spacecraft exploration, as some scientists have speculated about missions to orbit and study binary Kuiper Belt objects. The tidal evolution of binary systems in the outer solar system represents an interesting application of celestial mechanics. In binary systems where the two components are of comparable size and in close proximity, tidal forces can cause orbital evolution over time. The more massive component tends to gain angular momentum while the less massive component loses it, resulting in the separation between the components increasing over time. This process is slow, occurring over timescales of millions or billions of years, but it has implications for the long-term stability and evolution of binary systems. The study of binary Kuiper Belt objects provides insights into these processes and demonstrates how even the distant outer solar system is subject to ongoing dynamical evolution. The potential for future human exploration of the outer solar system, while currently constrained by technological and economic limitations, remains a possibility for a distant future. Concepts have been proposed for robotic spacecraft that could reach the Oort Cloud, though such missions would require either extremely fast propulsion systems or extremely long mission durations, potentially millennia to reach the outer boundaries. Alternatively, self-replicating spacecraft or arc ships designed to support human habitation during multi-year missions could theoretically explore the outer solar system. While such endeavors remain in the realm of speculation, they represent aspirations that reflect humanity's drive to explore and understand the cosmos. The outer solar system, vast and distant as it is, may one day become a destination for human exploration, though probably not in the foreseeable future. The philosophical implications of the outer solar system extend beyond mere scientific curiosity. The existence of this vast, largely unknown realm surrounding us raises questions about our understanding of reality and our place within it. For most of human history, the outer solar system was completely unknown, beyond the reach of human knowledge or speculation. Even in the modern era, our knowledge of this region remains incomplete and imperfect. This incomplete knowledge is a reminder that despite the tremendous progress science has made, vast realms of the universe remain mysterious and unknown. It encourages humility in the face of the cosmos and promotes continued investigation and exploration. The outer solar system represents not an endpoint of discovery but rather an invitation to continued inquiry and exploration. The spectral classification of Kuiper Belt objects through multi-wavelength observations has revealed subtle variations in surface properties that hint at different thermal and radiation histories. Objects showing redder spectra, indicative of increased absorption at longer wavelengths, are thought to possess surfaces enriched in organic materials that have been chemically altered by cosmic ray bombardment and ultraviolet exposure over billions of years. Conversely, bluer, more neutral-colored objects may represent bodies that have experienced less irradiation or have undergone recent collisional events that exposed fresh, unprocessed material from their interiors. This color variation among Kuiper Belt objects provides a paleontological record of sorts, preserving evidence of ancient processes and environmental conditions in their current surface properties. The phenomenon of contact binaries, pairs of bodies in close physical proximity held together by mutual gravity, appears to be surprisingly common among small bodies in the outer solar system. These systems likely formed through gentle collisions between smaller bodies followed by accretion, or through tidal capture of nearby objects. The contact binary configuration represents a transitional state. Over long timescales, these systems either stabilize into stable orbits or eventually merge through tidal dissipation. The study of contact binaries such as Arikoth provides insights into accretion processes and the gentle coalescence of small bodies that may have been important in planetary formation. The existence of these unusual binary configurations challenges earlier assumptions that collision events in space are necessarily violent and destructive. Instead, many collisions in the outer solar system appear to be sufficiently gentle to allow the participating bodies to remain in contact. The long-term orbital evolution of asteroids and comets, following gravitational encounters with planets, represents an area of ongoing research with implications for understanding the current distribution of small bodies. When a comet from the Oort Cloud is perturbed inward and passes through the inner solar system, it encounters the planets, particularly the massive gas giants. These encounters can dramatically alter the comet's trajectory, either ejecting it back to the outer solar system on a new orbit, sending it into the Sun, or placing it on a trajectory that brings it into the inner solar system repeatedly. Some comets may spend millions of years orbiting in the inner solar system before eventually being ejected or striking a planet. The orbital evolution of comets following their entry into the inner solar system is chaotic and difficult to predict precisely, but statistical models allow astronomers to estimate the expected distributions of cometary orbits. The ice giants Uranus and Neptune, often treated as secondary in discussions of the giant planets compared to Jupiter and Saturn, possess their own intriguing characteristics relevant to understanding the outer solar system. Unlike Jupiter and Saturn, which are primarily composed of hydrogen and helium, Uranus and Neptune are thought to contain significantly more water, methane, and ammonia ices mixed with rocky material. The term, ice giant, is somewhat misleading, as these planets are not solid bodies but rather have layers of increasingly dense material transitioning from a gaseous atmosphere to fluid interiors of mixed composition to rocky cores. The interiors of these planets are poorly understood and represent mysteries that would benefit from dedicated spacecraft exploration. The upper atmospheres of these planets show evidence of dynamic weather systems, including storm formations comparable in scale to Jupiter's Great Red Spot, indicating that despite their great distance from the Sun, these planets remain geologically and meteorologically active. The rings of Saturn and Jupiter, composed of countless small particles and small moons, represent a particular curiosity in the context of the outer solar system. While often discussed as planetary features, the rings represent a kind of miniature planetary system in themselves, with dynamics and evolution governed by gravitational forces and collisional processes. The rings of Saturn are particularly complex, with distinct ringlets and gaps whose structure is maintained through a combination of gravitational resonances with the planet's moons and collisional processes among the ring particles. The origin of Saturn's ring system remains uncertain. The rings may be primordial, formed with the planet, or they may be relatively young structures formed through the disruption of a moon captured in the recent past. The discovery of faint ring systems around Jupiter, Uranus, and Neptune has suggested that ring systems may be more common features of giant planets than was previously realized, though the rings of Saturn remain by far the most prominent and extensively studied. The magnetospheres of the giant planets, the regions of space dominated by their magnetic fields, extend vast distances into the outer solar system and interact complexly with the solar wind and interstellar medium. Jupiter's magnetosphere extends millions of kilometers into space, creating a region within which charged particles are trapped and accelerated to extreme energies. The interaction between a planet's magnetosphere and the solar wind creates shock waves and boundary layers that are sites of intense physical processes and particle acceleration. These magnetospheric interactions drive auroral displays on the planets, and create regions of enhanced particle radiation. The study of planetary magnetospheres provides insights into magnetohydrodynamics, the physics of plasmas and magnetic fields, and contributes to understanding of the space environment around planets throughout the universe. The moons of the giant planets, collectively numbering over 200 known bodies with new discoveries occurring regularly, represent an incredible diversity of worlds, each with unique characteristics. Beyond the large moons mentioned previously, numerous smaller moons populate the systems of the giant planets. Some of these small moons are captured asteroids or Kuiper Belt objects, while others are thought to have formed around the planet. The small moons often have irregular shapes, high orbital inclinations, and orbital periods suggesting recent capture or orbital evolution. The detailed study of planetary moon systems provides opportunities to understand accretion processes, orbital dynamics, and tidal evolution across a range of scales. The phenomenon of orbital decay, wherein objects gradually lose orbital energy and spiral inward toward their primary, is thought to affect some bodies in the outer solar system. Orbital decay can result from gravitational interactions with other bodies, from interaction with the solar wind or interstellar medium, or from tidal dissipation in certain configurations. Objects experiencing orbital decay eventually crash into their primary or into more massive bodies. Some of the small moons of the giant planets may be in the process of orbital decay, destined to eventually impact their parent planets, or to be disrupted by tidal forces. The process of orbital decay and impact represents a recycling mechanism, returning material to the planets from which it may have been scattered in earlier epochs. The measurement of surface properties of distant objects through remote sensing techniques has become increasingly sophisticated, allowing astronomers to infer detailed information about composition, temperature, and texture from observations conducted at Earth. Infrared imaging reveals temperature variations across object surfaces, indicating differential heating by solar radiation and differential cooling through radiation to space. Microwave observations probe subsurface properties, potentially revealing internal thermal structure or volatile reservoirs. Radar observations can measure surface roughness and material properties, distinguishing between smooth deposits and rough, blocky terrain. Combining these multiple observational techniques allows astronomers to build detailed pictures of distant bodies despite being unable to observe them directly at optical wavelengths. The concept of regolith, the layer of loose rock and dust covering the surface of celestial bodies, takes on new characteristics in the extreme cold of the outer solar system. The regolith of icy bodies in the Kuiper Belt consists of particles of ice and rocky material, potentially with significant quantities of organic compounds. The processes that form and modify regolith, impact fragmentation, thermal cycling, space weathering from cosmic ray bombardment and ultraviolet radiation, operate differently on icy bodies than on rocky bodies in the inner solar system. The regolith of cold icy bodies may preserve material in forms and chemical states that would be rapidly altered in warmer environments, making regolith samples from Kuiper Belt bodies particularly valuable for understanding the early solar system. The role of viscous spreading in the long-term evolution of planetary disks and debris systems has been explored through theoretical models and simulations. Planetesimals and small bodies in a disk experience collisions and gravitational interactions that gradually transport angular momentum outward, causing the disk as a whole to spread. This viscous evolution causes the inner regions of a disk to cool and contract, while outer regions expand and cool. Over millions of years, this process can significantly alter the structure and extent of a disk of small bodies. The application of viscous disk evolution models to the outer solar system suggests that the Kuiper Belt may be significantly more extended than it was in the early solar system, having spread outward over billions of years. The discovery of molecules in interstellar clouds that are identical to molecules detected in meteorites and cometary material demonstrates the chemical continuity between stellar formation regions and planetary systems. Complex organic molecules form in the cold, dense interiors of molecular clouds through gas phase and surface chemistry. When these clouds collapse to form stars and planetary systems, the molecules can be incorporated into the forming bodies. The same molecules then persist in meteorites and cometary material, providing a tangible link between stellar nurseries and planetary systems. This chemical inheritance demonstrates that the chemistry of life, based on carbon and hydrogen and the other essential elements, originates in stellar environments and becomes incorporated into planetary systems during their formation. The gravitational lensing effects of the Sun have theoretical implications for detecting very distant objects in the outer solar system, or even beyond. According to Einstein's general theory of relativity, massive objects like the Sun bend spacetime and deflect the paths of light rays passing near them. An observer positioned appropriately could potentially use the Sun's gravity as a natural lens to magnify and observe distant objects that would otherwise be too faint to detect. While this effect is well established theoretically, its practical application to astronomical observation remains limited by the difficulty of positioning observers in the appropriate locations. Nevertheless, the concept demonstrates that even the outer solar system's geometry can be leveraged for astronomical observations through application of fundamental physics principles. The concept of the habitable zone, initially defined narrowly as the region around a star where Earth-like planets could harbor liquid water on their surfaces, has expanded to encompass a broader range of potentially habitable environments as our understanding has deepened. The outer solar system, initially considered entirely uninhabitable due to its extreme cold, is now recognized as potentially harboring habitable environments in subsurface oceans and chemically active zones. This expanded conception of habitability suggests that the galaxy may contain far more habitable environments than previously imagined, distributed across a much broader range of stellar distances and planetary types. The implications for the frequency of life in the universe are profound. If habitable environments are common and widespread, then life itself may be far more abundant than humanity has historically assumed. The role of meteoritic delivery in enriching planetary surfaces with rare and siderophile elements that have affinities for iron and are thus concentrated in planetary cores, provides evidence of ongoing processes in the outer solar system. Despite the formation of planetary systems being largely complete billions of years ago, meteoritic bombardment continues at measurable rates. Late accretion, the delivery of material to planets long after initial planetary assembly, is thought to continue even to the present day, though at greatly diminished rates compared to the early solar system. This continuous rain of material from space affects planetary atmospheres and surface properties, and contributes to the ongoing delivery of organic compounds and volatiles to planets throughout the solar system. The question of whether solar system objects could host technological civilizations, while admittedly speculative, has been considered in the context of searching for extraterrestrial intelligence. Should life emerge in the outer solar system, particularly in subsurface oceans of moons or in the atmospheres of gas giants, the extreme conditions and isolation of such environments could limit the development of technology as humans understand it. However, organisms adapted to such environments might develop entirely different forms of technology based on chemical processes, biological engineering, or other mechanisms unknown to human science. The search for evidence of such hypothetical technological activity remains part of the broader search for extraterrestrial intelligence, though the practical challenges are profound. The atmospheric composition of Neptune and Uranus, dominated by hydrogen and helium but containing significant amounts of methane and ammonia, creates conditions in the upper atmospheres where remarkable meteorological phenomena occur. The methane in these atmospheres absorbs red light from the Sun, giving these planets their distinctive blue-green colors. The dynamics of the atmospheres of these ice giants remain incompletely understood, but observations suggest that they possess internal heat sources that drive atmospheric circulation and generate weather patterns. The energy driving this weather comes from internal heat, not primarily from solar heating as is the case for terrestrial atmospheres. The source of this internal heat is thought to be gravitational compression and the gradual cooling of these planets over billions of years. The long-term fate of the giant planets themselves, while vastly different from the fate of the Sun, nevertheless represents an important component of the far future evolution of the solar system. The giant planets will cool and contract over billions of years as they radiate internal heat into space. Eventually, over timescales of quadrillions of years, even the giant planets will cool to temperatures approaching that of interstellar space. The moons and rings of the giant planets will similarly cool and persist unchanged except for the very slow processes of space weathering. In this distant future state, the outer solar system will consist of a white dwarf sun orbited by the cooled remnants of planets and moons, a frozen monument to a star that once blazed brightly and generated the conditions for life to emerge.